This is the development of an off-grid solar lighting product. My name is Shelly and my partner is Joshua Vital. Our advisor is Kevin Shanley, and we are working alongside Selux for this project, a local lighting company specializing in exterior lighting. We have some objectives in terms of deliverables, testing, and system design for this project. Our overarching goal is to design a reliable solar-powered off-grid lighting system. So what does this mean? This means a lighting product that runs solely on solar energy. It consists of a light load, battery, controller, and solar panels. We aim to build and demonstrate a functional prototype by May of 2025. To do this, we need to ensure safe and efficient low voltage operation following UL safety standards. Our next objective is to select materials and optimize structural design. To do this, we need to test our system performance under real-world conditions. Finally, we will demonstrate a viable final prototype. Now we will discuss our current employed technologies. The main component for the system is a solar panel. We are currently working with the Renogy 100-watt solar panel. It's about 3 feet by 4 feet, and while it made a great component for testing, we will be using the smaller solar panel with the same wattage when we are past the bench testing stage. So what does a solar panel do? A solar panel converts sunlight into electrical energy. At Selux, we have a bench test set up with an artificial light that allows us to reproduce exterior environments to effectively test the solar panel's ability to create enough electrical energy to power our light system. Our system requires a battery in order to conserve electrical energy for later use. Converted energy from the solar panels gets stored in the battery during the day, and the battery releases the energy to power the luminaire after sunset. The battery is a necessity in order to be able to use the lighting system when the sun is no longer out. For this battery, we decided to use a nickel metal hydride battery. The thought process behind using this battery was depth of discharge, or DoD, which is simply how much of the battery you are able to use at once, as well as the safety of the materials used for these batteries. Furthermore, a large consideration of this project is days of autonomy, which is how many days the luminaire can run without consistent solar energy. So, in the case of a string of cloudy days, or for seasons where the sun isn't out for as many hours of the day, this is where DoD comes in. Nickel metal hydride served as a great choice for the system for these reasons.
The solar charge controller is a vital component of our off-grid solar lighting system. Its primary function is to regulate the voltage and current flowing from the solar panels to the battery, ensuring safe charging, preventing overcharging and undercharging, which are critical to the battery's lifespan. For our project, we chose a maximum power point tracking MPPT charge controller over a pulse width modulation PWM controller. MPPT technology allows the solar panels to operate at their maximum power point, extracting up to 30% more energy, most notably in low light and variable conditions. This efficiency makes it an ideal choice for our application. Furthermore, MPPT controllers can handle higher voltage inputs, enabling us to reduce power losses and optimize energy transfer to the battery. The programmability also allows us to fine-tune the charging profile, ensuring compatibility with our nickel metal hydride batteries and maximizing overall system performance. The microcontroller-based control system is the brain of our solar lighting solution, enabling precise control and adaptability. It processes inputs such as ambient light and battery status, using this data to generate a PWM signal that controls the dimming functionality of the LEDs via a switching MOSFET. This ensures that the lighting adapts to environmental changes and optimizes energy consumption. The microcontroller also supports additional features such as motion detection and time-based lighting schedules, adding versatility to the system. By combining these functionalities, the MCU ensures efficient operation while maintaining the reliability and flexibility needed for off-grid applications. This slide introduces the ongoing efforts in our project. At this stage, we are actively working on advancing both the software and hardware aspects of the system. These efforts will be elaborated on in the following slides, where we detail the progress and specific components being developed. Significant progress has been made in implementing a logic level to 24-volt dimming circuit, which bridges the microcontroller's low voltage signals to the higher voltage requirements of the LED lighting system. We've also developed a 24-volt to 5-volt regulator to ensure a consistent power supply to the microcontroller. These circuits are critical to the functionality of the control system, enabling precise dimming control and reliable operation. Moving forward, we aim to refine these circuits and integrate them fully into the overall system. Here we highlight the software progress we made on our control system. Our focus has been on implementing dimming control for the 24-volt LED load, which allows for precise brightness adjustments to meet different lighting needs. Additionally, we're developing up/downtime control mechanisms to manage the charging and lighting schedules effectively, optimizing energy usage and ensuring sufficient lighting during the night. We're also working on system diagnostics and monitoring features, which will provide real-time feedback on performance, enabling quick identification and resolution of potential issues. These advancements are essential for the reliability and efficiency of the overall system.
Here you can see some basic CAD models of our design. The pole design has had a bit of a hiccup this semester and will have to be advised by Selux for the rest of this project, but the overall pole manufacturing will be done through Salux's factory. More models and FEA analysis will be done in the spring semester. The majority of our fall semester was spent on testing and prototyping. Since we have a bench test set up at Salux, all the testing was done in the facility, with analysis being done to determine understanding and any next steps. For the solar panel, testing was done for power output and finding the best angle at which to mount the panels. It was determined that the power generated by the 100-watt solar panels was enough to light the fixture for up to 4 days. The amount of days of autonomy, of course, is also dependent on the battery. Thus, battery testing needed to be done as well. The depth of discharge of the battery was effective enough to be able to support this number. Another consideration for the battery was temperature performance. By allowing the system to run for a prolonged period, we were able to determine that neither the battery nor any other component had issues with overheating. This means that the specifications of the system were correct. Finally, the charge controller was also tested. It was imperative that we program the controller first to ensure it was running correctly and on profiles that are applicable to our application. We ran load regulation testing to ensure the controller could regulate the current running through the entire system. You may be wondering where we get the specifications for the system. Well, we put all of our calculations into an Excel spreadsheet and we call it the solar calculator. This spreadsheet has many pages and it will determine load size, it'll determine the battery size, it'll size the PV array, and it will even recommend solar panels for you to use. On the left here, you can see the artificial light we have been using for our testing setup. This artificial light allows us to mimic real-world lighting scenarios to ensure proper system specifications. On the right is a quick glimpse of the solar panel running with the test bench behind it. This was taken during an active test. On this slide, we have an enclosed electrical box. Since this is an exterior fixture, this box was created to protect all components from rain, snow, dirt, etc. It consists of the charge controller and fuses for each component. Every aspect of the electrical box is considered waterproof. In the spring semester, we will work with outside mechanical engineers to develop a new design, preferably a smaller and more narrow design to fit existing poles.
Testing is a critical facet of our project, ensuring the reliability and efficiency of the system under real-world conditions. For the lighting system, we are conducting tests for brightness, power consumption, dimming functionality, and overall reliability to verify that the system meets performance expectations. On the control system side, we're testing adaptive brightness functionality to ensure smooth and responsive adjustments to environmental changes. We are also conducting time-based control tests to validate the scheduling mechanisms for charging and lighting. Lastly, Sensor integration tests are being performed to confirm accurate motion detection and ambient light sensing. These comprehensive tests will ensure our solution is both reliable and energy efficient.
Thank you so much for watching.